probably one of the most important that you have to understand or to solve if you want to see nuclear energy play a more substantial role going forward. And we have the perfect person here today to discuss this topic with us. Rod Adams I'm really glad that he was willing and able to come and visit. He graduated from the U.S. Naval Academy in 1981 with a bachelor's degree in English. He was accepted into the nuclear power community by Admiral Rickover. He served on the USS Stonewall Jackson as a junior officer in a variety of billets, and then as the engineer officer on the USS Von Steuben. After 12 years of naval service, he resigned his active duty commission, entering the Naval Reserves, and founded Adams Atomic Engines Incorporated. In 1999, after 6 years of entrepreneurial activity, he was recalled to active duty and served again until his retirement as a commander in 2010. During his second active duty period, he gained experience as a teacher, financial analyst, maintenance analyst, headquarters staff officer, and program manager. And he's now the publisher of Atomic Insights and the host of the Atomic Show podcast. We've had a wonderful visit today, very interesting discussion, and I'm not going to say any more because I'd like us to have a chance to hear Rod speak. So please, Rod, the floor is yours.
All right, my first announcement, I hope, is a welcome one to students, is I'm not going to use any PowerPoint. There was a time in my life when I was teaching, and I kept hearing my students talking about death by PowerPoint, and I kept recognizing that many of my colleagues, and I had fallen in the same trap, as it would, spend all of our time trying to build these outlines and whatnot and get them just perfect so that people could read them, and then we would spend our time reading the slides to you. So I decided that probably wasn't the best way to talk about something I think needs to be understood as almost a story, a narrative. Nuclear energy started off at the very beginning with really no focus on cost. No focus on keeping cost under control. It was a brand new technology that was being supported by lots and lots of government spending. And the idea then was, let's figure out how to make this stuff work, and we'll figure out the cost later. We'll figure out how to produce systems that are economical later. For a time, nuclear engineers were taught that when it comes to nuclear safety, cost is no object, and that's still true. That in a safety environment, cost is not the biggest component, but there are ways to control cost, ways to design to keep your systems simple enough, cost effective enough that you can actually compete. It doesn't do any good for us to say that we have the greatest thing since sliced bread. Actually, we have a world-changing technology that can produce lots and lots of power with no greenhouse gases, no air pollution, solves the world's problems on supplying fossil fuels if we can't produce a product that can get out into the marketplace. There was a time when we worked hard after the first atomic era to figure out how we can address this problem and build systems that are more likely to come in on schedule and on cost. It wasn't just the nuclear industry. There was some cooperation between the nuclear industry, regulators, academia that said, okay, what can we do to make this a more controllable technology that we can actually build a schedule, we can predict what things are going to cost, and we can turn that into a customer that's happy with what they got. One of the things that we did was we recognized that in the first atomic era, there was some places where people who fundamentally didn't want nuclear to succeed had the ability to come into a process and add delays, add uncertainties, and get even to the point where in one case, we finished the plant. the Shore facility in Long Island, and that plant, after costing $6 billion because it was delayed multiple times, was not allowed to operate. So that's probably the most expensive electricity ever produced is $6 billion divided by 0 kilo. Okay. It becomes an almost undefined cost per kilowatt hour. Okay, so during that first era, when we were building plants, one of the ways costs kind of got out of control was that once the plant construction process got started and under a lot of momentum, the vendors and the utilities had almost a combined motive for not keeping costs under control. Vendors recognized they probably weren't going to sell too many more units. So, for them, keeping their revenues came from finishing the units they were building and getting as much revenue as possible from each unit. For the utilities, they recognized that their model was a whatever the capital cost was plus a certain fixed profit is what they're allowed under their utility regulation. Well, if that's your model, the more fixed capital investment you make, the more profit you make each year. So the incentives were all kind of in the wrong direction. As time went on, we also had the regulators who were helping the industry figure out where things were not working as well as they should. And the regulators were coming in and saying, we need to add these particular capabilities, we need to make modifications to address certain issues. And then the vendors were saying, okay, that means I have to redesign my system to make that happen. Or I have to go back and take things apart and add new things to address the regulatory issues. That again added to the cost spiral that happened. Those modifications took time to design, they took time to implement. The regulators had the utility to the point where they were almost over a barrel. They simply had to agree to make the changes because they'd already spent hundreds of millions to billions of dollars and still needed to get permission to operate. So the industry, government counterparts tried to figure out ways to address these cost problems. Here's the things that they really focused on. They said, if we simplify the designs, that may help us to reduce the cost. We keep things simpler, that anything that we can take out of the system, if something doesn't need to be bought, doesn't need to be tested, doesn't need to be qualified. So that was a good thing. If we can reduce the number of places where opposition can come in and slow the process down, we can reduce the cost a little bit. Okay, we can make the schedules more predictable. So in that case, the thought was, this two-step licensing process that we had, where we got permission to build, we went ahead and built to what we thought we were going to do. We made some changes along the way. At the very end, we said, okay, now we'll go back and get permission to operate. The two-step licensing process was viewed as a very risky process with a lot of cost implications. So the utilities and the regulators said, okay, we'll devise this new one-step licensing process. Spent a lot of time working on that and figured that was one of the ways to address this uncertain cost attachment. Decided that we would make some evolutionary changes rather than real radical changes, because the idea was we already had this infrastructure built up to build light water reactors, so radically changing that would add too much cost. So we said, okay, we'll just do a little bit better of what we learned how to do before, and we'll just, make that happen. Applied some PRA insights. One of the things that happened in the first era was that probabilistic risk assessment was done after the fact. It was done after the plants were already designed. It was implemented as a result of accidents. So people said, well, if we can do PRA during the design, we can make changes that make sense and keep the risk of accidents down while recognizing what parts of the design really have an impact on that. Well, we can make some changes. We can use the risk-informed analysis to streamline the process. Added some modularization. People said, if we can get away from stick-built, now, and in this case, I need to make sure it's clear to people, modularization doesn't necessarily mean small units and one complete module, and second complete module, and third complete module. What it really meant in this case was building plants with what some people call a skid type construction, where you have a section of the plant and you put that all together in the factory, and then you ship it to the site and it matches up with another section of the plant. And so it's like you do with home construction. Some people produce modules that all together, each one is different, but you put them all together on site and suddenly the whole system comes together. That was kind of the idea of the AP1000 and the ESBWR are designed with modularization, where you can do a lot of the work in a remote factory and ship the complete units to the site. Started thinking that 4D computer modeling was going to help reduce costs, because a 4D model allows you to integrate in the component of time and see how you actually assemble things and build a schedule that is more integrated across the path. Now, the AP1000, when they were doing their design work, they actually built a 4D model and determined after running their model that it was only going to take 36 months to build an AP1000, which means you can do almost anything you want with a model. All depends on your assumptions, right? Passive safety was thought of as another way to reduce the overall cost of nuclear by reducing the number of active backup systems and redundancies that you had to have, and different trains of protection. And then the part of the one-step licensing process was to add in this idea that we would certify a design, certify the reactor design one time and be able to use it for multiple projects, and you can just incorporate the design in from another project into your design. A lot of effort was invested. Okay, there was a period in the 1990s where it looked like there might be an opportunity for nuclear to come back in force. After the Persian Gulf War, oil prices got high, natural gas prices got high. There was people who were saying, maybe we need to go back and look at this nuclear thing again. Westinghouse, and there was a program to help certify some early designs. Westinghouse came up with the AP600 design. Started doing design work for that in 1986. Filed the paperwork with the NRC in 1992 as part of a program to test the one-step licensing and the design certification. There was a couple of others, the ABWR, System 80 Plus from Combustion Engineering, and some of the ideas that we've been talking about recently with how to address cost were also talked about there. Smaller size, AP600 was a 600 megawatt reactor, thought of as, hey, maybe if we do things a little bit smaller, we can not scare the customers away with too high a price at the beginning. By about the mid-90s, the price of natural gas had dropped to $2 a million BTU, and there was very little interest on the part of utilities in this mid-sized reactor that had been certified. So the AP 600 got completed, got certified by the end of the 1990s, but by that time, you know, it had taken 7 years to go through the design certification. The market was no longer there. Nobody really cared. The price per kilowatt hour was still too high. So what's the best thing to do if the price per kilowatt hour is too high at 600 megawatts? Make it bigger, right? Scale it up. That's our normal response to a situation where we're not competitive. We scale it up. So, you know, Westinghouse looked at the AP 600 and said, yeah, we've got that certified. We've gone through this whole process. We learned a lot over the last 7 years. What's the cheapest way to reduce the cost of this? Scale it up and try to use exactly the same philosophies, the same methodologies, the same design parameters, and even in some cases the same scheduling. And we've already convinced the NRC they're going to accept this, so we'll just scale it up and do it all over again with a bigger design. That was the response to the cost challenge then. After all that effort, this is started off in about 1986 and went all the way up until the Energy Policy Act of 2005, when we said, okay, now we've got a situation, we think we can get nuclear out there. We've got these new designs that have been certified and ready to be implemented. And so now we've got this under control. And what happened again? Started projects, and those darn natural gas people. Okay, they had their prices up nice and high. We thought we could compete against $8, $10 a million BTU gas, and all of a sudden gas dropped down to $3 a million BTU. The target changed considerably. And we've got to the point now where after all these efforts to reduce costs in the standard ways, we still have people that can make some of the following statements about nuclear energy, and statements that I can't really argue with. Amory Lovins calls nuclear energy so hopelessly uneconomic that one shouldn't debate whether it's clean or safe. Joseph Rahm says it's too expensive to matter for the foreseeable future. And Bill McKibben, who is the head of 350.org and telling people to divest from all their fossil fuel investments and all that stuff, says that nuclear energy is like burning $20 bills to make electricity. Unfortunately, like I said, it's hard to argue with that right now. Okay, we've got some, and even I'll give you another one. The strongest advocates. So the World Nuclear Association says nuclear power plants are expensive to build, but relatively cheap to run once you get it built. So what went wrong? With all this effort, I mean, people worked really hard to reduce costs, to try to get this under control, to try to get it so schedules would be able to be predicted, that people wouldn't be able to stop a project that was good and just make you walk away. What can we do? Are there solutions that can be implemented in time to matter? I want to talk a little bit about Plant Vogtle, and VC Summer is kind of the same. It's just they're a different bit of site, but I've been able to visit Plant Vogtle. I've got some friends on the project, and they've been pretty honest with me about what's been going on, so I want to share some of the things that I learned about it. I want you to remember that the AP 600 was the predecessor for the AP 1000. There's not really a whole lot different. The design began in 1986. The first design certification was filed in 1992. The final safety analysis was issued in 98. It was design certified in 99. And then they started the process over again with the AP 1000, which had an objective of trying to keep as much as you can of the AP 600 to keep the overall design cost down and keep the same construction schedule, the same modularization scheme and all that.
Would you explain what Vogtle is?
Okay, Plant Vogtle is a place in northeast Georgia, where there are two AP 600, AP 1000s under construction. It's owned by Georgia Power, which is a subsidiary of the Southern Company, and Oglethorpe Power in the city of Dalton, Georgia. VC Summers, another plant 50 miles away, also building two AP 1000s. Those are the only new plants that are under construction in the U.S. There is a TVA facility called Watts Park 2, which was initially started in 1973, I think. It may come online sometime at the end of this year, early next year. Okay. So Plant Vogtle is two AP 1000s, new modular design plants that have been certified and are under construction under this new idea that we ought to try to keep nuclear costs competitive.
But also, you've got a bunch of them being constructed in China much further along, so a base of experience in construction that should in principle help.
And there are, in fact, some of the same issues that have affected Vogtle have affected some of the units in China. So the AP 1000 was finally was certified in 2006, and that was the design under which the contract for the Vogtle facility and the VC Summer facility was signed with the utilities. They were kind of going on the fact they had a certified design, and they built a schedule and had that schedule being certified by the public utility commissions. And very early, about another year or so later, the NRC imposed a very significant rule change that required them to adhere to the aircraft impact assessment rule and had to go back and do a redesign. Okay, so right at the beginning, that regulatory creep that we talked about earlier, we hadn't really got a control over that. We got a big hit from the change of regulations. It was based on events that happened in September of 2001. NRC finally implemented the rule in 2009 and applied it to anything that wasn't already under construction, which of course at that time Vogtle wasn't under construction. It didn't apply to any of the operating plants. It didn't apply to Watts Bar, whatever, but it did apply to Vogtle. So in order to adhere to that regulation, Westinghouse had to redesign the shield building, and that delayed them a bunch. It's not been the only issue though. That the combined operating license for Vogtle, 2012 finally with the redesigned shield building, and within a month after they started the project and announced the schedule, there was a 6-month delay already announced right then. The companies have already, by May of 2012, both the vendor and the utility had started filing lawsuits to point as to who was at fault for the cost and schedule problems. And then most recently, and this is not good news for people who are strongly in favor of nuclear energy and very interested in nuclear design, most recently it's been announced that Vogtle, which was initially scheduled to start up in April of 2016 for Unit 3 and April of 2017 for Unit 4, will be starting up in sometime in 2019 for Unit 3 and 2020 for Unit 4. I attribute the first maybe year to 18 months delay to that aircraft impact assessment rule, but that's not all of it. There's more. One of the things that happened was that the engineers who evaluated the soil conditions apparently didn't do a good enough job from the point of view of the NRC. They had unexpected soil conditions at Vogtle, an unexpected amount of soil that had to be taken from someplace else and brought into the site because the soil wasn't good enough to meet the design requirements. So that added a little bit of time. The people who did the rebar placement for the base mat used a standard, a concrete standard that was not exactly the same as the concrete standard specified in the design certification document. Okay, in the nuclear world, you gotta follow specifications. If you don't follow your specifications, you can add a tremendous amount of cost. And in this case, it took about 7 months to resolve the issue of rebar placement. There was also by using the wrong concrete specification, there was one more piece with the rebar. There are several ways to tension reinforced concrete. One of them is with a hook at the end of your bar, and the other is to thread a cap at the end of your bar. So they used the threaded cap. The specification in the DCD said a hook, so that added some more time. Some of the large modules, we talked about modular construction, some of the large modules that have been designed have not met quality specifications for various reasons. The team that was building the project set up a facility in Louisiana, brand new facility, had not done nuclear grade work before, and had some quality assurance problems. That same facility was just down the street from a large number of liquefied natural gas projects. Some of the same skilled labor that could have been working on the modules at the facility for Vogtle decided that the LNG facility is paying better, and they moved away. There's some turmoil in the labor pool. Eventually, and the other problem is that, and it's a challenge for some of you guys, the engineering that was specified for the modular designer has been called into question because some of the people said, hey, you didn't make this so I can actually build it, okay? Your specifications for how this is put together and what the tolerances are or how the access is, whatever it was, you didn't design it so it can actually be built. You didn't coordinate with a manufacturer during the time you were doing your design work. Okay? That's another challenge that sometimes seems, hey, we can get this design done if we just don't have to talk to anybody about how to manufacture it.
Do you have any sense whether that was really it wasn't manufacturable, or whether the tolerances are going to be a pain to the manufacturers that they decided to delay? There's two sides that might be.
Yeah, well, there are pieces of it that were simply had to be re-engineered to be able to be manufactured because they didn't have the capability of getting access to with the specified welding machines and that kind of stuff.
But presumably, a year or two in advance of this, very similar, except for the shield building, because the Chinese chose to retain the original sealed building design for the first few units and then switch to the aircraft resistant one. But presumably, all of this stuff was being manufactured in factories in China and deployed in the field. Why was there not a transfer of lessons learned from that activity to the U.S.? Or is it just different enough in China in terms of labor costs?
It's a good question. I think that there has been some module construction problems in China as well.
Yeah.
And I'm just not sure if they got learned early enough to feed that back into the U.S. or what the transfer of knowledge was between them. Some of the problems are simply that the facility at Lake Charles is not up to the task.
Yeah.
That's been some of the,
Because
it was a new facility, they didn't have the right management, they didn't have the right QA programs, and whatever else, yes.
Wasn't the problem that it wasn't a new facility, it was a converted shipyard? And they already had management at Lake Charles who thought that building a nuclear power plant was like building a modular ship.
I'm pretty sure the facility was new, the managers may have come from the modular shipbuilding, because that is a big industry down in that area of Louisiana. I'm pretty sure the facility itself was built specifically to build the modules.
I mean, the thing that I had expected to happen, and which shows that you've got serious quality problems, is that if you mess up the first few of these things, they're all unique in the fact that each module is designed, but it's the same fabrication approach. So if you can't, by the third or fourth one, have corrected what your problems were with the first few, then you've got a much more serious problem on your hands. And that points to major problems with labor force and management.
Yeah. Essentially what was happening was the modules were being delivered to the site, and the modular assembly building on the site was being used to remanufacture the modules at the site. Okay, I've had the privilege of going into the room where they were doing this and seeing what kinds of things they had to fix. And again, the bottom line for the project is they've now moved a lot of that module construction work to other facilities, including Oregon Iron Works, Newport News Shipbuilding, Toshiba, a unit in Japan, and IHI Corporation, which is a small partner in the Westinghouse project, also in Japan. So now instead of having one facility, they're going to have 4 facilities producing modules to try to catch up a little bit. But in each case, when you think about going from one supplier to another, now you've got to go and transfer the drawings, you've got to qualify their supply systems, you've got to have them scale up their workforces to do the work. It adds a delay to this.
What are typical modules?
What do you mean, what?
Well, you say you build a module in the factory and then bring it out.
Well, the module will have piping systems, heat exchangers, pumps into this system that has framework and supports, and that will be transferred to the site, and then that module will all the piping systems will be set up so they connect to piping systems from other modules. The wiring goes through there. They have, so it's essentially building a big, and these are large, 40, 50 feet tall in some cases, maybe 40 feet by 40 feet in diameter and depth and width. And so they have to fit just right to be used. So the modularization has added cost so far. Now I've talked to people on the site. They believe that once they get the modularization done and get the quality in, it's going to compress the construction project considerably. That's yet to be proven. Let's see, some of the corrective actions for this, there's really been no change in this lengthy design certification project. I don't think that when we were looking at one-step licensing as an industry, people thought of it taking 7 years to get a design certification or 8 years to get a combined operating license. I don't think that was part of the plan, but that's really what it's turned out to take. The ESBWR finally got a design certification a couple of months ago. Again, it took about 7, 8 years from the time they filed it. So right now, the NRC is saying, well, we've got the process, just, industry, keep using it, we'll get better at it. Well, at some point, people say, well, what's the payback? Of course, the vendors that have made it through the process don't have any interest in helping smooth the process for the guys behind them either. There's a growing recognition that the one-step licensing may not be the right choice for first-of-a-kind units. Even with the delays that we've had so far, there's still a big opportunity for intervention as the testing programs go into play, and it was called the ITAC, Integrated Test.
Acceptance tests and acceptance is critical.
Right. inspections, tests, analysis, acceptance criteria. You know, you have to meet all of those things to say that you actually built to the design that you got certified at the beginning. All right, so there's still a lot of uncertainties. So where do we go from here? How do we accept, what do we do now? What, you know, the industry said it was trying to learn and it told everybody that we've got cost under control and we've got schedules under control and we're gonna do a lot better this time than last. And quite frankly, we aren't doing it. So what do we do different? We can't just say, well, other people are expensive, other sources of electricity are expensive, because that doesn't necessarily wash. You've got to be able to look at yourself and say, well, what do we do? We need to figure out how to design for cost, how to get cost out of the system completely so it doesn't come back. Simplify and really figuring out what things that we can do will make a big difference. We've got to figure out what the big costs are. We've got to look and say, what are the real drivers? Where do we add costs? What kinds of specifications are we giving to people that make it hard to meet the quality standards? You know, were the challenges of getting these modules done, were it really that they weren't going to work well, fit well, and all that stuff, or was it simply that the specifications were tighter than they need to be? I don't know. Sometimes when you're writing specifications, you have to make allowances. You know, make sure that you don't say that the surface of a 60-foot tall vessel has to have absolutely no scratches on it. You know, if that's not necessarily required. So you got to think about whether your specifications are what's really important, to make sure you tell the vendor at the beginning what they have to do. Work closely with them to make sure that your systems are going to meet the specs, and start early. You know, there's a lot of things that were should have been able to be tested during the time when the design certification was being reviewed. But of course, until you get your certification, how much incentive do you have to do a lot of investing and testing of your building processes? As an engineer, one of the things I hope that you all do is try to be cooperative with those who are trying to figure out where the costs are. Don't grouse too much about feeding the database, okay? That people will ask you to keep track of your time and your effort and your estimates, so that you can build a system that allows you to identify where the costs are so you can try to get them out of the system. One of the things that designers often are not very good at is recognizing when the choices they're making are adding cost in some other place, where a system that you say, well, this is exactly what we need to solve my problem here. You forget about the impact that system change will have on other people. You may have added another pump or two, which now changes the battery requirements for after shutdown battery supply, and now you've just added enough capacity requirements so that the building no longer fits all the batteries that you need. And so now you need to maybe expand the building to adjust for your change in a pump over here. Sometimes we're not very good at communicating and saying, how does my change affect others? Design needs to be an attempt to optimize for the system, not by component. And unfortunately, sometimes in our design teams, we have to assign people to focus on a particular component, but you need to have pathways and communications established so that people recognize where their impacts affect others.
The related thing, establishing well-documented design bases so that you can trace back why things were done the way they were, And when you come in suggesting you might want to make some changes or modifications, that certainly was not done well in the first generation, the plants operating now.
In many cases, we completely have lost track of our design bases, and another thing that happens in a project, it doesn't, it's not something that engineers can control very well, but project leaders should, is it's people will make blanket design decisions at the very highest level without recognizing what the impacts of those design decisions are throughout the project. For example, I worked on the Empower project for about 3 years. One of the design decisions that was made at the very beginning of the project was we would like to follow Edward Teller and Ralph Moore's suggestion to put all reactors underground. Okay? That, hey, that's the right way to do it. That if you put the reactor underground, that eliminates people from complaining about that ugly old reactor. It, it protects you from aircraft impact. It reduces your shield building requirements. All those things. Just put it underground. And then the next thing they said was we want a passively cooled system. Okay, natural circulation. Natural circulation, for those of you, I've talked to some of you today, recognize that necessarily requires a tall system. Okay? You need to have a good delta H to drive the circulation. Okay? So now you're going to take a tall system and put the whole system underground. Okay? And that.
And then you put it next to a river.
Well, then you put it. Well, you want to put it next to a river or an ocean so you have a nice cooling source.
High water tank.
I grew up in the state of Florida, so I was always concerned about this idea of putting a tall system underground because we don't even have basements in Florida because we're afraid they're going to flood. If we build a car garage, it's above ground, not below ground. So that notion of a tall building underground. Also, it's not really the visual impact of the reactor building that is a big cost driver. I'm not sure that in most cases people don't complain much at all about the reactor building because if you all have seen pictures of sites without any cooling towers, you recognize that a nuclear plant is pretty darn small to begin with. If you're right up close to it, the building looks pretty big. Pull back just a little bit, you say, wow, it's not a very big building. 12 stories, 13 stories tall, something like that. Not a big deal. So the other thing is people didn't think about the fact that once you go underground, you think, oh wow, the ground is shielding me. Well, wait a minute, the ground is actually pushing against my building. So I've got to have a structural system that keeps the soil pressure from pushing the building and actually wanting to float the building up. So I've got to, it actually, in our case, the thickness of the concrete at the base of the design was thicker than it would have been if it was out of the ground and meeting aircraft impact requirements. So, sometimes you got to somehow figure out ways to communicate with project leaders when you're recognizing that things are driving your costs. Okay, this decision to go completely underground, maybe there's an optimal solution. Keep the core underground and let the rest of the plant be above ground. Core is really all you want to protect against aircraft impact, for example. There's some confused incentives in the nuclear world. We have this model of vendors, customers, utilities, and then constructors. Really are the three big players in a project. Okay? And they all have different incentives. The vendor wants to vend. They want to sell as much equipment as they can, or at least produce as much revenue from selling equipment as they can. The constructor wants to construct. If it doesn't really, they don't mind if we come up with a design that puts the reactor completely underground. So that means you got all this excavation you got to do. You got all this concrete you got to pour. You got all this rebar you got to put in. You build. So the constructors want to construct it. That's what they make. And of course, the utility wants to produce electricity. and sell electricity, and they would prefer for all those things to cost as little as possible. So there's some confused incentives, and part of this incentives has been so imposed is dysfunctional. You know, all of those different motives cause nuclear projects to almost inevitably end up in court. Okay, people suing each other. Hey, that cost increase was due to, you know, you changing the foundation design, or you didn't tell us the soil, or you know, you didn't recognize that the NRC was going to change the aircraft impact rule, or you know, whatever it is. But you know, there's a lot of money at stake and a lot of suits. Yeah.
Are these all first of a kind problems that the next one that gets built will just go smoothly ahead with all the fixes that have been worked out? First plan.
To a certain extent, yes. There are, you know, there's two different first of a kind systems, and quite honestly, Unit 4 at Vogtle and Unit 3 at VC Summer. VC Summer only has one plant operating right now, so it's Unit 2 and 3 under construction. The second of those is going along much better. Okay, that's the really good news. Is that, in fact, it's going along so well in some cases that they have to slow down the first one so that the second one doesn't overcome and pass it. Okay? Because if you're fixing stuff that you said, darn, you know, you can actually do it right the first time because you already know what, you know, you already know how to pour the base mat and you can pour that correctly the first time, and all of a sudden the one that was supposed to be the second unit is actually possibly could be the lead unit. But then you just go back and forth, and so they're slowing down the second unit so that there's actually a little bit of delay time and enough time to learn and implement.
But that's clear evidence that there is some learning from experience.
There's absolutely learning from experience. I mean, most of the things I talked about here, if you think about it, you should recognize these are kind of the one-time early shots, but these are projects where making a mistake early is big dollars. Okay, the total cost of these 4 units under construction is roughly $25 billion.
I'm just curious, why didn't they do 2 first of a kinds simultaneously? Rather than taking one of them and let them say, you go first by 6 months, and then I'll follow.
Well, actually it was. Vogtle was supposed to get started earlier. I think they're close to each other because Vogtle had the excavation and rebar problems.
That and the fact that the design certification took so long that VC Summer, which had planned to be starting later, by the time that the design certification finally got issued and the COLs got issued, they got issued at the same time. The design certification.
If I was VC Sumners, I would have said, okay, lead guy's behind by 6 months. We're going to slow walk and not start for 6 months.
Yeah, it's a question. It's a good question. And again, part of the challenge is, you know, the first of a kind. In this case, you know, we're at first of a kind units that are 1,200 megawatt plants and a $6 to $10 billion project for one unit. Okay, it makes it so making mistakes is very costly. You know, in the first nuclear age, we actually did walk before we ran. We had the opportunity to work hard on small plants first as we scaled up. We had a lot better chance of training workforces and as we're scaling up. So it was a little bit different. And maybe we should have recognized that, you know, we really no longer knew how to build plants, or we needed to build the budgets bigger. But, you know, already when you started saying that 2 units was going to cost $14 billion, that's a pretty big chunk to get approved. And so there is some incentive to not build too much contingency in there. And actually, in both Georgia and South Carolina, the public utility commissions don't want the projects to build contingencies in. They want you to have to come back and get permission to accept a higher cost. Okay, I'm going to give you what I think is a more constructive path, what we ought to be driving for to try to get some better control over these costs so that we can let the nuclear technology flourish. We need to work somehow to align the team so that they all have the same incentives to get the project produced with an efficiently designed, low cost to operate system. Because there are times when, I mean, you can lower the initial cost and add to your maintenance cost if you're not careful. You really don't want to do that unless you happen to be a vendor who knows that the only way to make money in nuclear, or the consistent way to make money in nuclear, is to sell a plant and then sell all the spare parts and services for the rest of the life of the plant. Unfortunately, talk to vendors. What's that?
That's where Westinghouse makes its money.
They know that.
Yeah.
Okay? GE knows that. I think there's some people in here are doing some work on defense systems. Defense contractors know that very well. That, you make money on the spare parts and the services, and you make money sometimes by bidding low and making money on change orders. I'm serious. You will. If you're in an honest engineering group, you'll find out that people will say that. Yeah, we make our money on change orders. So do exactly what the customer says they specify, and then let them know that what they specify is not going to work. So think about, where does the money in the electricity business really come from? The money comes from the people who buy electricity. Okay, that's the revenue generator, selling electricity. So somehow you got to align your team so that everybody makes more money if you sell more electricity, and you're the low-cost producer of a vital commodity. Okay, the low-cost producer of a vital commodity is a company or the group, the team, that makes the most amount of money. Some of the most economical and reliable nuclear plants that are operating today were built by companies that did their own construction management because they were very good at it. Whether it be EDF or Duke Energy, I think Florida Power and Light did that down in Turkey Point. They did their own construction and management and really managed the projects to keep the costs under control, and to get the quality that they needed to make sure the plant had the longevity.
Ron, a quick thought on that. The utilities today that are really competent at doing major capital equipment replacement also have figured out really good practice in terms of how you manage those sorts of activities. And then you've got others. There's one I'll leave unnamed to the south of us. You don't. And that may be one thing to look for in terms of management skill. It's those utilities that are good at fixing their plants may be the ones that are going to be good at building new ones.
Absolutely. So the best designers and builders of facilities to manage data don't sell facilities, they sell data or data access. Most innovative petroleum drillers, they sell oil, not equipment. Best designer of equipment for making razor blades, sell razor blades, not equipment. It's okay, I must be out of time.
There's a class.
Okay. All right. One more thing that I think would help the nuclear business a lot is if we could try to work hard together to change the paradigm, change what the NRC recognizes as its mission. And we don't even have to change the mission, we just have to change the way they read the mission. The mission is the NRC licenses and regulates the nation's civilian use of radioactive materials to protect public health and safety, to promote the common defense and security, and to protect the environment. unfortunately, they've always read that mission as to protect us from radioactive materials, and not necessarily recognize where radioactive material use improves all of those things. How we can better regulate to more safely and effectively use radioactive materials and radiation to promote the common defense and security, make us a more prosperous nation so that we have the ability to, protect ourselves, have an indigenous supplies of energy that aren't controlled by others, that we don't arm our opponents by paying elevated prices for their products, and then have to buy from them if we want to fight them. That doesn't make sense. But, we want to protect the environment. If you don't generate electricity with nuclear, what are you going to use to generate electricity? It's going to be something that is more environmentally damaging. I can't think of a power source that is less environmentally damaging if done correctly. And we need to, protect public health and safety. Well, there's accidents and public health impacts from the competitors of nuclear energy all the time. As I was coming from the San Francisco airport to Berkeley, I passed through it was a stop for San Bruno. I've heard of that place before. Anybody remember what happened in San Bruno?
Gas explosion.
They had a natural gas explosion. I mean, a gas pipeline going through a neighborhood blew up.
The cleanest hydrocarbon source, the most environmentally sound hydrocarbon.
Well, it's the cleanest fossil fuel, yeah. So, but it is explosive, flammable, and there's a good reason why we use it. So there's some fundamental cost disadvantages. Some of you all are working on other systems that don't have the fundamental cost disadvantage of light water reactors with their very high pressure coolant systems and a very detailed quality assurance that has to be put into making sure that that coolant boundary remains intact. A very challenging quality assurance job of making sure the piping, the pumps, the valves, the pressure vessels, everything else in that system remains intact, and that's one of the first things of a safety-related system is the primary coolant boundary. Building pressure vessels and all that is extremely expensive. Specifying them, specifying the welding, all of that adds a very high layer of cost. So if you can figure out a way to use a low-pressure system, one that is more friendly to materials, that may be a good way to address. Higher temperatures may give us the ability to have higher efficiencies so that we can get more power out of the same reactor thermal input that produces potentially cheaper electricity. More robust fuel cycles. We have a cost disadvantage of having to keep bringing in new fuel and finding a place to store the old fuel. Although, quite frankly, the fuel cycle is one of the more economical parts of nuclear. We've got that pretty well down. We don't have leakers anymore. Our fuel costs are pretty low. Roughly 70 cents a million BTU, or what, that 0.5 cents a kilowatt hour, pretty low. The heat engine is a possibility. The steam plant and the construction process to build the steam plant for nuclear plants drives an awful lot of the cost, a lot more than people think. The nuclear island at the Empower program was going to be running around 20% of the cost. The other 80% was a secondary plant.
Was that because it was nuclear specific, or is that what it costs the coal and the natural gas guys too?
Well, the steam plants for a nuclear plant are more expensive because the feed water systems have an impact on reactor safety. So the feed water and the steam up to a certain point has an impact. So those parts of the system are a little bit.
So if we can system engineer it so that the steam can't create a safety problem, then we're.
Absolutely.
Okay.
And I have some colleagues who are working on ways to better decouple the heat engine from the heat source, and so that you can vary power and do changes in the secondary system that have no impact on the primary system, and believe they can separate the regulation, but that's to be determined. Yes.
Traditionally, there used to be a rule of thumb that the NSSS contracts was 10% of the total cost.
That's about right.
So that means that 90% is balance of plant. And
construction.
what surprises me is that nuclear engineers are completely ignorant of the balance of plant. They don't think they need to know anything about the balance of plant. That's something for mechanicals and electricals to do. But if you don't have good mechanical and electrical design, you're not going to build a nuclear plant.
Absolutely.
What do you say is the balance of plant? Steam generator and,
It's actually mainly rebar and concrete.
we got people that built a beautiful bridge. We can line it up.
Yeah. The nuclear steam supply system is just the primary components, the structures, not the structures, the supports for those. The structure is a big part of a nuclear project, the seismic buildings, and of course, control rooms and the ventilation. I mean, ventilation is a much bigger deal than I imagine. You know, it's safety-related ventilation to keep the control room habitable so that in an accident situation, you can still control the plant. But, it's just all kinds of things drive your costs, including, you got to supply power to the fans to keep the control room occupiable under an accident condition. So. All right, final thing, when you're doing your cost estimations, one of the reasons that we have cost overruns is we don't necessarily do a good job of estimating what the cost is going to be. Don't underestimate costs. One of the things that people do if they're doing cost estimation is they will figure out the total of all the things they know and say that's the cost. But that means that all the things you don't know, you just assign a zero cost to it, which is a bad estimation. Figure out what works, reuse things when you can, make incremental changes, and try to use things that are actually in commercial production, not, we've got one of a kind over there, that proves the concept and we can just use it. Because if you've got a proof of concept and then you want to use it, you're going to bring in a lot of additional costs.
So let me note first, there is a class that comes after this, and the students that were exiting were heading off to their class along with their professor. A couple of questions, and then we can have them more informal. So maybe starting with.
What can we learn from the Bureau of Naval Reactors? They don't seem to have these problems, or is it that it's classified and we don't hear about it? Or are they just better than the civilian people?
Recently, the Naval Reactors has always done a decent job of coming within their estimated costs. Part of that is they don't underestimate the cost. They tell Congress what things are going to cost, and they make sure that they can do it within that cost. They're not, they don't lowball, so things do cost more. However, over the last, say, 10 years or so, the Navy has worked really hard to reduce the cost of submarine construction, including the cost of the nuclear plant. Some of the things that they did was they've done modularization in a way that makes it work. Now, they were driven to do modularization for a political reason. The political reason was they didn't want all of the construction work being done at one facility.
One congressional district.
Right, they needed to spread that work out, so they actually had some modules being produced up in Connecticut and brought down to Norfolk. So but they learned how to do modularization. They recognized that building 2 per year saves a tremendous amount of overhead compared to building 1 per year or 1 every 18 months. So they got the Navy to buy into that and have funded 2 submarines a year for the last couple of years. And they've got the cost down that way. They've got some very sophisticated lessons learned and ways to reduce the complexity of systems. So all those things have come into play.
Can it be transferred to the civilian side?
Well, a lot of the knowledge is transferred, but the direct knowledge won't be transferred unless there is a political decision to tell naval reactors that an engine is an engine, it's not a weapon. Okay? And, you know, naval reactors have been, for the last 50 years, under the assumption that naval reactors are weapons or part of a weapons system, and they shouldn't be common knowledge. Now, my personal belief is that other than the silencing part, the stuff that makes it quiet, they're just an engine the same way as we transfer jet engines from fighter jets to commercial jets all the time. You know, that's nobody, you know, no, commercial airplanes that run on jets, no civilian company had to build those from scratch. They were able to transfer what they did for defense systems. You know, that's pretty standard.
Yeah, thanks for your talk, Alan Boland. So you're talking about the issues of design, and you mentioned some examples of people not thinking about how their design will impact something else. I have some personal experience with that particular problem and solving that problem. I worked at Ingalls Shipbuilding for a couple of years, and I was involved with the requirements design for the auxiliary direct cargo ship, which never got built, and also the DD-21, which became the Zumwalt class, right? And so I was involved in the requirements management for both projects. And the way that you design ships, and they're very complex systems just like nuclear, just maybe less quality grade, is you write the specifications down in a Word document.
Mm-hmm.
And there's no way in the world that you can possibly expect something that complex to not have conflicts, particularly not with keeping track of why something was done. I mean, you don't see that in a document. You just see the document, the end result. So, you know, one of the things the Navy was trying to do was do exactly that using computer software to put all that information in and keep track of it. And they were borrowing software from the design, from software companies who were using the software to design software. But this was like 15 years ago. So tell me, you know, do you know, are these companies attempting to employ this requirements management and use newer software and things like that, or what? Because otherwise I don't see how it can happen. I mean, you can talk about it, but you can't fix it.
Yes and no. I'm very familiar with what you're talking about. In the project I was working on, we were using, I can't remember the name of the actual package, but we were using the requirements management tools that Lockheed Martin and a few others used when they're doing defense work to manage requirements for certain parts of the system. In other cases, we weren't. And by the way, the project I was working on is no longer being funded. So it's an example of what not to do in some cases. So yeah, requirements management and actually detailing what you're trying to do, why you're trying to do it, what, you know, impacts it has, what linkages between requirements is something that you can do better with software. You know, still is a very difficult challenge, but in some cases it is an investment that does pay dividends down the road.
Okay, one more question.
Yeah, so So the increase of cost due to the change of regulation, as you mentioned, is kind of a result of the non-economical factors such as the concern for safety. So do you think that kind of cost is actually predictable or can be estimated? And the more general question is how you compare these economical factors and non-economical factors.
Yes, it's important to recognize that there is an improvement in the resistance of the system to the impact of aircraft by going with the design change. That there was pressure from the public to make that happen. Now, in my view, the thing that the nuclear industry needs to do is make sure that everybody understands that that was an improvement that was mandated from outside and really shouldn't be attributable to our inability to control costs. Haven't done a good job of making that case so far as I know.
It's also, that one ends up being like the first of a kind cost, because the shield building construction with the new methods
It's actually going to be better,
is going to be cheaper and easier than with the
as
conventional.
long as we can
rebar.
sell more.
Yeah, but the problem is that now the Florida Power and Light is probably a lot less likely to consider adding 2 AP1000 units at Turkey Point, because they were very serious about doing that, unless they can convince themselves that these are first of a kind problems and their original estimates on cost are still valid for building more.
Yeah, well, you know, again, it's really hard to kind of slough off and say, well, those are first of a kind costs, because they may be the only of a kind.
Last of a kind.
Yeah, the last of a kind.
Yeah.
And unfortunately, by the way, something I didn't want to talk about, but the last of a kind always gets more expensive for very human reasons, okay? You know, if you don't have another project to go to, how motivated are you to finish the one you're on?
But then there'll be new AP1000s built in Europe too, so, which,
The welders aren't going to move to Europe, I can guarantee that.
hopefully the lessons move to Europe.
Yeah, but the welders aren't going to move
Yeah,
to Europe.
that's
So
correct.
that's what I'm saying, the last of a kind in a particular location, they're going to be expensive, because the welders, the pipe fitters, the constructors, they all have good reasons to keep that project going,
Yeah.
which is why Watts Bar has taken as long as it has.
So then the,
Thank you.